So it's a pleasure to have here as a visiting professor in this program that we have now in ICMM, Professor Hasan Sahin. There is, I mean, I know him like since he was doing the postdoc in Belgium, but he did the PhD in Bilkent University in Turkey. There is a highly prestigious university in Turkey. And then he did 4 years postdoc in Antwerp. Antwerp?
Yeah, Antwerp, yeah.
Amberes, I think it's in Spanish. And then he moved to the Izmir Institute of Technology, where he's now vice dean in the Faculty of Science. You have the chair, no, of the institute, no, of the ICTP ICAR.
Yeah, yeah.
Okay. I mean, regarding the, let's say, a little bit of the numbers, let's say, of, like, to tell you like how good Hasan is. I mean, like, we are not now like promoting too much, like taking a look to the just pure metrics, but to get an idea. It's not easy for a theoretician to have like the productivity he has. Like he has published over more than 150 papers. And if you take a look to his latest publications and the impact they have, like the number of citations is really outstanding. I mean, I'm not going to enter into like the details, but it's really a pleasure to have him here. And his research team in the Izmir Institute of Technology, the CENT, the Computational and Experimental Nanotechnology Group, conducts theoretical and experimental research to identify and understand fundamental physical mechanisms underlying the surface, interface, and transport behavior of crystal and molecular materials. And today he's going to talk about these chemosensors, based on two-dimensional materials, combining, as I said, experiments, which is kind of unconventional for a theoretical group, and theory. Thank you, the floor is yours, and we are super happy to have you here.
Thank you.
And by the way, as an announcement that, I always said when talking about Hasan, he has like really high quality and talented master students in the group all the time. Okay, so like whenever you have an opening, you're looking for talented students, I think you can contact him and he will point you towards a good student. So we have the
physicists, chemists,
both of them. Yeah, I will show some pictures of those guys. Yeah. Yep.
So it's good to keep the email in there.
For me, it's okay.
Okay, I think we're going to keep it like this. Yeah, sorry.
Okay, so thank you for nice introduction and thank you for invitation, first of all. And it's always a pleasure to be here with you. And whenever I come here, I learn something new from you. And I know ICMM means share. So in my mind, ICMM guys, they share what they know. So it's very nice. Because we know some people, they hide. So I'm very happy to be here. And so this time my talk, will be about chemosensors. And I just recently learned those sensors. And as you know, I'm a theoretician. And we calculate something for structural optimization. As you see here, this is fluorographene, and approaching atom is kind of transition metal atom. And in the end of this calculation, I can say that this surface is not that stable according to the DFT calculation. As you see here, it's trying to be substituted with 2 fluorine atoms from the surface. So this surface is not that stable against transition metals. By performing DFT calculations, one can have such conclusions. The second thing is we can calculate what is the electronic structure, whether material becomes insulator or metal or semi-metal, half metal, whatever it is. So you can calculate even before your experiments. You can have some insights. And phonons. I like phonons much because they are fingerprint of material, and you have fingerprint of material theoretically. At the same time, if you can measure those fingerprints, then you can be sure about your results. You can be sure about your scenario, and it's a good way of concluding your results. I mean, if you have something about phonons, then you can use the knowledge to understand your structure. And so theoretically, one can calculate XRD spectra of any given material. It's easy. And the next thing is stability analysis. Now I'm heating up the monolayer of chlorine atoms, just a fantasy. So nobody expects the presence, stability of monolayer chlorine, but it's just expectation. This is the calculation. So based on quantum mechanics. Oh, sorry. And sorry. Yeah. And this calculation says that no, it's not that stable at room temperature. In several picoseconds, it will be destroyed. So don't expect it as stable. And we can calculate what will happen to your molecules if you create a device, molecular device. So what will happen? Maybe you can expect some spintronic properties from that device, and we can calculate it. And the last thing is maybe the most important one is optical response. From theoretical point of view, calculation of optical response is easy. Just calculate the dielectric constant, frequency dependent dielectric constant. Then if you know epsilon 1 and epsilon 2, then you can calculate absorbance, reflectance, and transmission spectrum of any material. And yep, by using DFT, I did some calculations. I learned something new. For example, once the topic was mussels, and we love them, we eat them, and you know they are kind of superheroes. They have super talents. They stick on a surface, and you cannot remove them easily, even in the water. So they have a super talent. So what is the talent? So they have some sticky organelles, so it was exciting for me, and the impact of the journal is not that important. And just I was there, and I understood that by using DFT, one can understand why mussels stick on a surface. Because from computational point of view, it's easy. So in the end, what I understood is, so it has some spatial proteins, and those proteins, they stick to every surface. But if there are some water molecules around, so they use those water molecules to bond more strongly. So what makes them special is those proteins, that's all. In the end, we understood. So I was very happy. Another thing can be something else, like perovskites. And perovskites was very famous. Actually, they are still famous. And so this is cesium lead bromide. And when you shine on them with UV light, they are emitting green light. Famous cesium lead bromide. And we did mangan doping. In the end, we noticed that it becomes orange colored. So it was emitting orange color. So we changed something after manganese doping. And in time, I think in a week, it changed its color. So in the lab, I saw that it's emitting blue color. So what happened to the material? So we had small nanoparticles, orange color emitting nanoparticles, but in the end, they turned into something else. So what was happening at the atomic scale? Because I can calculate something at atomic scale. Then, you know what was the scenario? It seems that when I tried to dope it with manganese atoms, I was using manganese dichloride salt. So since I was using manganese dichloride, so those chlorine atoms, first of all, they substituted with bromine atoms. So it seems that I got cesium lead chloride. Instead of bromine, I got cesium lead chloride. And cesium lead chloride emits blue light, as here. But in the beginning, I had orange color instead of blue. And why? Because I I had some manganese atoms inside, and those manganese atoms, because of their unpaired electrons, we had some mid-gap states, electronic states, and so if you have mid-gap states, then the emission becomes more red colored. This is why, because of manganese atoms, presence of manganese atoms, I got orange color, and in time. So you know what will happen? What happens? Because calculations said that actually I couldn't dope it. Actually, I couldn't dope it. So manganese atoms were there for just 3 days, but in 3 days they went up to the surface. And after some XRD analysis, we saw that at the surface we have formation of mangan oxides. So you see. Simple calculations, and I know I can explain whole the scenario. So I like studying like this. And
excuse me,
please.
What type of calculation did you do there?
For example, here an electronic structure calculation. So if you perform electronic structure calculation, so I have cesium lead bromide, and together with manganese atoms, I calculated the energy band diagram. And then if you remove manganese atoms, you will have no mid-gap states in your energy band diagram. And another calculation was molecular dynamics calculation. I inserted manganese atoms inside the cesium lead chloride and bromide. Then I started heating up the material up to the room temperature. Then I noticed that manganese atoms, they don't stay in a certain place. They are very small, and they diffuse easily, and they don't prefer to be bonded in the material. And so we saw it from molecular dynamics calculations, and in reality, actually inside there was no manganese atoms. We just saw manganese oxides at the surface. Yeah. So after muscles, we had perovskites, and one of geothermics guys from our university came with a question, and he was asking about these silicates, and they are working on geothermal energy, and you have some hot water, including heavy metals, and you have to transport it from one place to another place. But meanwhile, you are having such silicates, and depending on where you are, the type of silicate changes. I mean, using calgon, that doesn't work for every silicate. You have to find another type calgon. So, and his question was, and this is the silicate of a certain place of Turkey, but they didn't know which antiscalant was better. Then we performed some calculations, some very, very simple calculations, just binding energy of a molecule on a surface. And we calculated some molecules, and I suggested that PEG, PVA, PAM, and PVPA, they can be good for removal of such spatial silicate. And then they performed some experiments by using some mixtures of those things. Because if you have bromine inside the silicate, your calgonate, your antiscalant will change. If you have some bismuth in the silicate, you have to use different one. So you see, it's a very different area, but DFT works. Just the theory guy needs to know what experimentalists say. So that's all. If you understand, then it's easy. Or you can predict a new phase. I was there. I was a lucky guy, and maybe you know Sefahattin, my collaborator, my friend. So his question was, there is something weird about rhenium disulfide. He said that they got some weird results. They expect some similarity with molybdenum disulfide. This is the top view, as you know. And after my calculations, I noticed that rhenium disulfide is not a semiconductor as other TMDC materials. So it's a semiconductor, but with a direct band gap. And structurally, so it has a very different type of structure with a distortion. So in this paper, I contributed to that part. And you see, for experimentalists, sometimes it's not that easy to determine what is the atomic structure there, because it's very thin, it's invisible. And but from theory, you can have some hints about the structure. So here they were happy in the end because everything was clear. And then I suggested formation of this dimerization. Then after some high resolution TEMs, they got this. They confirmed this dimerization. Then the scenario was complete. So you can use DFT in different fields. We have some experimental part in the lab. Since I got bored a little bit with theoretical calculations, I started learning those things. And we have some simple chemical exfoliation and wet chemistry part. It's a bench, actually, simply. And I was lucky, I borrowed one of my friends' Raman spectrometer. So I have some rich friends, and I borrowed this, and it's working well. And I have a very simple optical spectrometer, and I can measure PL, absorption, reflectivity, and transmissivity. Then I can compare with my calculations. Why not? And so finally, I started working on sensors. So this is my group, and there are some new guys. And so I'm working for Department of Photonics. And my students are coming from photonics department, physics, electronics, and some guys from chemistry. But in the end, they all learn DFT and some experimental things that I learned. I mean, so those guys one day will be searching for a group for PhD. So I will definitely tell them about ICFM. So recent results, and it will be about chemosensor. So simply, chemosensor, you have source and drain, and in between, you have a surface, and there will be current passing through this surface, and you will be monitoring the current. And this current, this base current, will be changing with coming gas molecules. Just, it's that simple. And we have some Keatley tools. So we will be measuring the current, and we will applying some bias, and our device will be like this, and this is the sensing surface. It's the most important part. And we have some such kind of interdigitated electrodes, and here we have a sensing surface. And so we are working on printing devices. Because I noticed that from one student to another student, devices are very different. So I said, come on, let's print it. Otherwise, every time we get weird results, different results, then it was very hard to understand. So we are printing devices. And so after my visit last year, I learned that paper substrates are better. So, and after some inspiration, we started working with paper substrate. They are cheaper. And we have graphitic electrodes. Again, they are cheaper. So, and we have those things, and just we are changing this part. So this part can be graphene and molybdenum disulfide. And so in last 2 months, we started working on platinum diselenite and mangan phosphor sulfur materials, because these materials have some magnetic properties, magnetic ground states. So maybe their magnetic ground state will be useful for their sensing applications. We are searching for it. Let's see. And the study one. Study one is about sensing alcohol responsibly. You should sense it responsibly, please. You know that movie, huh? Famous movie. Okay, we will sense alcohol. Why? What's the motivation? So this is ethanol. So chemistry people knows better than me. And the chemical formula is here. And the molecular shape is here. And the cocktail, you can prepare nice cocktails using ethanol. And also it's possible to prepare your cocktail by using methanol. Why not? And you see molecular shape is almost same, just 3 atoms are different. Just 3 atoms are different. And if you look at methanol containing cocktail, same. You cannot differentiate. And they both look same and nice. So which one to drink? With ethanol containing drinks, your party would end up with some hangover. Not bad. But if you have methanol, so methanol poisoning can cause blindness, organ failure, even death when recognized too late. You see, in the end, it differs too much. So please sense it. One has to sense it. So this is the motivation of sensing ethanol or methanol. What about the results? So the first result, so mainly what's the mechanism? We have a base current. I set it to 0. Base current, it's 0. And then there's an increase because of incoming methanol and ethanol towards the surface, approaching molecules. And so there is an increase. Sheet conductivity of graphene, molybdenum disulfide, whatever it is increased because of increased charge density. So because of electrostatic interaction with the surface, and there's a charge transfer between surface and molecule, then you see increase in the base current. It's simply like this. Then my question is, so both ethanol and methanol leads to increase in the base current, but their signals are different. So you see, so what is the reason of difference? So this is an important question for me because I'm thinking about understanding at atomic scale. I'm not more into the devices, working devices. I need to understand. So why the signals are different for ethanol and methanol? So these are charge densities induced by ethanol and methanol. So calculations say that methanol interacts with the surface so more strongly. Why it is interacting more stronger than ethanol? Because of its dipole. It has a larger dipole. So since methanol has a larger dipole, it has more interaction. So there is more charge transfer for methanol. This is why it's simple. So after calculations, then I can say it's simple because we have confirmation. You see, if you are working with graphene, this is N-type doping and this is P-type doping, and so increase in sheet conductivity is larger for methanol because of higher polarity. So higher polarity so shifts the Fermi level more. Then the question 2. The larger the concentration, the higher the increase in the base current. We see it. And actually it's something expected. As expected, larger concentration of organic compounds would lead to a larger P-type doping of graphene. So larger P-type doping, larger concentration of charge carriers, then you can expect this increase in current. But you see, it's not increasing that much. It's the third question. So in time, it seems that ethanol and methanol behaves in different ways. Why for ethanol I'm not having such increase? Instead of this increase, I'm having almost saturation with ethanol. Again, calculations. So while methanol molecules prefer to cover the surface as much as they can do, for ethanol molecules, there's something strange. So when you try to cover the surface with ethanol molecules, they start to combine together, they form clusters. And those clusters are tend to detach from the surface. This is why, since they are detaching from the surface, so after forming clusters, you see, so after here, it seems that they formed clusters, so they are forming clusters detaching away from the surface, and at the same time, there are some newcomers, new ethanol molecules, but you cannot increase the number of ethanol molecules on the surface. It's not possible. But for methanol molecules, so of course there will be some saturation points somewhere there, but because of this tendency, they behave in different ways. Okay? So we answered several questions. Those questions are simple, but one has to answer to go further. And the second study is again about chemosensors, but this time it's about being CVD or not to being CVD. So you can prepare your sensing surfaces in different ways. It can be CVD graphene, CVD MOS2, or it can be exfoliated one. Do they differ? This is the question. Let's see. Okay, so now I'm just sensing methanol molecules, and I know that methanol molecules would lead to an increase. So you see, here we have just nitrogen, and when methanol comes, there is an increase in the base current. Again, I'm cleaning the surface, then whenever I apply send methanol molecules, there is an increase. So this one is for CVD graphene. I see increase. If I'm using perfect, almost perfect graphene surfaces as a sensing platform, I see increase. But if I do the same with exfoliated, so it's chemical exfoliation actually, not mechanical one, chemical exfoliation. So chemically exfoliated graphenes, you see, if I send methanol gas, there's a decrease. Again, decrease, decrease. Repeatedly, there is a decrease. You see, your device is behaving in a very different way. So which one is correct? And what's the reason? Then we need to understand why they are behaving in a different way. Some characterizations, as you see, we have AFM image. So AFM image of CVD and exfoliated are quite different. Here we have some patches, a lot of patches, flakes, but in CVD we have nice surface. So again, S10 measurements and Raman signals. You see, we have very nice, almost single crystal graphene, but here, because of fragments, flakes, we don't have that sharp peaks. And so this slide says that those materials are not same. They are different actually. They are different. And some calculations. So binding energy of methanol on the surface of CVD graphene, it's high. So larger binding energy means that there will be some electron transfer. Then you will see the effect of those methanols in your current. Okay, we know that. And you see, binding energy of methanol with armchair edge, again, it's high. Binding energy of methanol with zigzag edge, and again, zigzag edge. So I'm showing calculations for zigzag edge 2 times because, you know, for graphene, you can have ferromagnetic edges or antiferromagnetic edges. So both of them can, if you are performing your experiment at room temperature, you can have both of them. This is why, to not miss this scenario, so to make it complete, I calculated for AFM and ferromagnetic case. But it's not, they are not that different, so binding energy is still high. And this part is important. You see, if you have CVD graphene, and if there is an approaching methanol molecule, then there is a charge donation from graphene to methanol for CVD graphene. And for edges, you see, if you have armchair edge, and if there is approaching methanol molecule, there is a charge donation from methanol to edge. It's different. It's vice versa. And for zigzag edges, you see, for one of them we have charge donation from methanol, and for the other one from edge to methanol. But you see, if you have exfoliated graphene, you have lots of edges, lots of edge states. So they will play a role, and you see what's the dominant effect? The dominant effect is charge transfer from methanol to the exfoliated graphenes. But if you are dealing with CVD graphene, just charge transfer will happen from surface to the methanol molecule. Okay? So now we understand why they behave in different ways. Yeah, please.
Those charge transfers, they are, how confident are you of their accuracy, because they are rather small? And,
Yes.
And where, this is always a problem with calculating charge transfers, right? Where do you put the boundary between what is graphene and what is
Yes.
your absorbent?
Yeah, good question. Yeah, here the question is how you count your number of electrons around the molecule, around the graphene. So the technique here is Bader charge technique. We use it. And after using this technique, actually, first of all, we tried the sensitivity of calculations with replacing molecules in different points. So at every point, at every side of the edge, we see same behavior. You are correct. So every DFT calculation is a kind of approach. So numbers are not exact, but just approach. But the tendency, we see that the tendency is always like this. The number 009 can change if the molecule is here. It can change. It can be 007, 005, but the tendency is not changing. Please.
For chemically exfoliated graphene,
Yeah.
and the Raman spectra are very clear for that. Not only you have plenty of small grains and boundaries and so on, you must probably have also oxygen functional groups on the, for sure. So my question is, perhaps you should take into account this point. So the chemically exfoliated graphene are quite plenty of disorder, oxygen functional groups and so on that may have also a role besides either size of the
Yeah.
graphene grains.
Yeah. So far we didn't consider that scenario, but maybe you are right. And actually, if I would see any hint, any clue for presence of oxygens around, I would consider it. But yeah, so in Raman spectra, there is no peak for graphene oxides.
Yeah.
This is why.
The spectra you have are indicating that you do have, most probably, you have functional groups. The resistivity, the conductivity is lower because the resistivity is higher, the resistivity, because it's less P, the sp2 carbons, there are also sp3 carbons. So I suspect that you may have also oxygen.
Yeah, it can be considered.
Okay.
Yeah.
And along the same lines, I think it would be very unlikely to have such clean edges in the zigzag. I mean, most probably they are functionalized somehow.
Even hydrogenation can be expected. Yeah. You are correct. Yeah, it can be considered. Yeah. So, actually, I'm talking about the same thing. So, two different studies, but the topic is same: charge transfer. It's just the mechanism is charge transfer. If you are tuning the direction of charge transfer, then you will change the response of the sensor. It's that simple. Okay. So, in this slide, whenever you send your methanol molecules, you obtained an increase in the base current. Why? So in the beginning, CVD graphene was p-type doped like this, and after charge transfer, it became more p-type. So becoming more p-type means that around the Fermi level you have more number of electronic carriers, and in the end you have an increase. And the second thing is, if you have exfoliated graphene, so again you have p-type material. The exfoliated one always behaves like p-type, but this time because of the direction of charge transfer you have less p-type doped material, less p-type doping, then decrease in the base current. This is why you observe this decrease. Then the scenario is complete, but yeah, if I consider presence of oxygens and other things, it will be more complete, let's say. And so it seems that, so theoretically one can understand those things from theoretical point of view. It can, by using DFT, it can be calculated. And so conclusions, graphene and graphene-like structures with their clean basal planes, they are good materials for sensing applications. And there are some simple questions in those devices to be answered, as we see. And response and mechanism of a sensor must be understood at atomic scale. It seems that because they differ. Just changing number of atoms differs the response. And the DFT methodology can be effectively used for such problems. And I say, cheers, it's better with ethanol as a conclusion. So thank you very much for listening. Please.
Thank you, Hasan. Just one question.
Yeah.
So the way you perform this experiment, so you have your printed electrodes,
Yeah.
and then you just drop the ethanol or methanol directly,
Yeah.
dilute it or not dilute it, or in a chamber which is with a pressure control or not, because the evaporation.
There's no pressure control and no dilution.
Okay, I'm telling this because of course you will have an equilibrium between the evaporation, so the molecule in the gas phase and the molecule
Yeah.
in the liquid
Uh-huh.
until it evaporates.
Mm-hmm.
And the polarizability of these molecules may change upon if there is water in the ambient, and so they may change the polarizability.
Yeah.
Solvatation, which is the ability to mix with water around,
Mm-hmm.
and all these may change very much the way they
Yeah.
have the stronger acidity of acidity.
Mhm.
Yeah.
Yeah.
This can make a difference.
I think so.
How the ethanol and the methanol
Yeah. Yeah.
behaves.
Yeah. I think so. And
But then is it drop casted, or
Yep.
is it gas?
Surfaces are drop casted for some examples, but we are sending gas molecules. Just we have tubes and we are sending ethanol and methanol.
So you bubble?
Yeah, bubbler. Yeah, we have a
that's
bubbler.
like air or nitrogen
Yeah.
through ethanol to bubble it.
It's
right?
not. Yeah, it's not liquid.
Okay, okay.
Yeah, it's not liquid. Yeah. Yeah, we clean the surface and then again we apply ethanol.
Yes,
Yes.
I understood that it is more or less in gas, so no?
Mm-hmm.
Okay. It is interesting that in the example of methanol ethanol,
Uh-huh.
which is for me surprising and very interesting, is that really it's possible to eliminate all methanol and ethanol as soon as you eliminate, or because the conductivity goes down to the initial state. So it is surprising that everything is evaporating, no?
Mm-hmm. Mm-hmm.
It's like that.
Yes. Yes.
In spite of the strong coupling of the surface with methanol, it is eliminated as soon as you eliminate the input of methanol.
Yeah. And so they have van der Waals type bonding with the surface. So this is why when you send nitrogen gas, so you can clean. So since there is no chemical bonding with the surface, so this is why we are able to clean.
Possible to clean only with
Yeah.
nitrogen. And rapidly.
Yes, very rapidly. In several seconds,
Okay.
they go away. Yeah, you're welcome.
I was actually,
Mhm.
thank
Yeah.
you very much for the talk, and I was actually wondering, connected to this material effect, so whether you have actually done along like multiple cycles, and what is the performance as you go to, through
Yeah.
those cycles, and will you see a duration perhaps in the sense?
Yeah, device performance is something that I need to learn, but I see that those devices are not that stable actually. If I perform the same experiment tomorrow, then because of increase in the resistance, it becomes very high, and because of oxidation, it seems that. So so those devices are not that stable at the moment. So in time, I'm sure that it will be not working. Yeah.
Last question.
Yeah.
White paper, because it's cheap. White paper. Why do you use paper as the substrate?
Because of Andres. He inspired me. Yeah. Because of lack of money, the first motivation. Second motivation is Andres, and
I mean, paper. I guess it's not so stable, perhaps, no?
yeah, you know, we need to think about.
Because it's very cheap, so it's an interesting point.
Yeah. So I newly entered to the area, and I said, let's start from the correct side of the area, because in the end, one has to design a device in a cheaper way and it should be environmentally friendly. So this is what I learned from those guys, and so this is why I started from that point. It's cheaper and it's more environmental friendly. Yeah.
For gas sensors as well, paper actually works as a really nice scaffold. So because you basically have all this fiber structure and so on, so that we have a really good effective area.
Okay.
Right, so you
Mhm.
so but it's true.
And the sensor is the graphene you put on top? In fact, no?
Yes, but the paper, so it's a scaffold for the
For the
graphene that you put
Okay,
in.
yeah.
So you cover the fibers with it.
It's graphene, CVD graphene, in this case also, or it is in the methanol, ethanol, it's
Yeah, it's CVD. Yeah.
Okay, you have transferred it up to paper.
Mm-hmm.
Okay.
And you sense mainly with the top surface, right, of the CVD.
No.
Also like at the.
No. So like you can go as deep as 20 microns. So like the typical structure of a normal paper is like fibers of 20 microns in diameter. So like the active area of typical devices is 20 micron-ish.
But the graphene goes down to the...
So the printed one for sure. The CVD I don't know, but the printed one it can really
printed
solve
one.
it.
Okay, fine.
How you transfer the CVD graphene on paper?
You know, I don't remember the details, but you know, first they grow it on a copper surface, then they use iron 3 chloride, something,
It's a wet
yeah.
transfer, so that's
Then
why-
use some tweezers to transfer it. It's an easy process.
Easy.
So my students told me that it's easy.
For the students, I'm
I have never done it, yeah.
No, because after like you clean with iron chloride,
Uh-huh.
and you transfer it on water, but if you put the paper substrates in water, it will be wet and it would be more difficult to
Uh-huh.
pick up the CVD growth, and to not break the CVD graphene, you cover it with PMMA or I don't know, photoresist something. So then you have to also
Yeah.
clean that part.
Yeah.
So I don't know how you did.
Yeah. Here the good news is the device behavior is same with some other substrates. It doesn't have to be paper in this case. Silicon dioxide, use silicon dioxide or sapphire. Then the physics will not change. It will be same.
Yeah, I was just curious about like how you manage it.
So we have to write the students again.
With the silicon, I mean,
Yeah.
it's easy, it's rigid, so you just use
Scoop it, yeah.
Yes,
Mhm.
but with the paper, I mean, it will get wet immediately.
Maybe they don't fish it with the paper. They put it
Yeah.
with some
We don't-
pieces
We don't put the paper
You
inside the
cannot
water.
pick up the CVD graphene
and you
layer.
have the PMMA.
Doesn't matter. I mean, you can't cover it like that thick, otherwise you can't clean it. So it should be like thin layer on top of the graphene, because in the next step you will clean it with acetone or
But then you will solve the
ethanol.
paper with.
Yeah,
Need acetone, yeah.
and you can't pick up it like this. So you have to like do the fishing.
Mhm.
So you have to give us the contact of the student.
Okay,
because this
keep
is
in
not,
touch. Keep in touch.
It's interesting.
Pablo?
Pablo, yeah.
It was nice talk. Very enjoyable. I was curious about
Uh-huh.
defects. So
Defects.
what would be the difference between CVD graphene and like let's say beautiful, perfect, mechanically spherolytic graphene with like ideally no defects.
Yeah, the defects behave like edges. So we considered, yeah, they behave like edges. Because if you have defects, then you have some unpaired electrons at those sites. So they behave like edges.
Go to defects.
Yes, yes. Yeah.
Because then, I mean, you're using CVD graphene, right? Which has certain amount of defects.
Mhm,
So
mhm.
I would expect that then the response that you have is actually due to defects, right?
Yeah.
Or really interaction with the cleans, like carbon-based surface.
Yeah, in the whole response, the number of defects is important. So if you have just 1% of defects on CVD graphene, then in the end you will have CVD graphene-like response. Okay.
Yeah, but what I find interesting is the competition between, like, if the effect in defects is similar to edges, and edges like drop down the current,
Mhm.
then you have competition between the molecules that are on the surface, on like nice carbon surface,
Mhm.
and the ones that are on defects. The one goes like the current up, and the other one
Yeah,
like
yeah.
drop the current down. So
That's the reason why in the liquid phase introduction you have the opposite, because you have more edges per surface
Yeah, yeah.
area, right? If I understood correctly.
Yes, yes. And
yeah, but in CVD then you have a competition on both things.
yeah, even
Far away.
No,
Yeah.
no, in the defects.
Defect, yeah, depending on how effective it is.
so defects are like edges. And think about exfoliated graphene. So every exfoliated graphene has also edge like CVD, so surface like a CVD graphene. But its surface, so more than its surface, it has edges. So this is why edges, effect of the edges win in exfoliated case. So there are always hierarchy between number of edges, number of perfect surface atoms.
Yeah, but it was more about like, let's imagine like infinite layer, right? So no edges. So like you could control the sensitivity of your sensor according to the defects, right? Like the more
Yes.
defects,
Yes,
the
yes,
more
yes,
current
yes.
up.
Yes, it's possible. Okay. Yep.
Yeah, question by side.
Yeah.
So like these kind of like sensors, they're physics sorted, right? So label free
Mhm,
sensors.
mhm.
They're nice because they can be recovered, you know,
Yeah,
like,
yeah.
like you don't need to functionalize
Mhm.
with the specific acceptors and so on. But they always have the drawback of the selectivity.
Mm-hmm.
So in this particular case, you're lucky
Yeah.
that the behavior for two different molecules is different.
Yeah. Selectivity looks possible here.
Yeah. So, but then, like, one strategy people use in order to like distinguish different molecules without selective sensors is to fabricate sensors with different active materials,
Mm-hmm.
and then you use pattern recognition in
Mhm.
order to distinguish cluster. Let's say, like
Mhm.
then this is acetone, this is ethanol.
Ah, yes.
You know, like you have like different. So, like you have make an array. Let's say, like
Mhm.
4x4
Mhm.
devices with 16 different materials, and then you use some kind of like training algorithm in order to do this kind of thing.
You see, he's inspiring me. So,
I'm telling you because we have here somebody like with artificial intelligence
Yeah, yeah.
background, so maybe you folks you should.
yeah, so since I'm not a experimental guy, experimentalist, so since I'm not a device guy, so I'm learning those things. And if you have any idea, so please help me. We can collaborate on those things. I know I need to learn a lot in this field. Yeah, and selectivity is something else. So we need to. We are studying on it actually. And
Because you can operate without a selective sensor as long as you have like many sensors with
Mhm.
different, you know,
Yeah,
different behavior.
yeah,
Then
yeah.
you use some kind of like
Yeah.
pattern recognition algorithm in order to.
yeah, why not? Why not? Yeah, one day. So in time, I think we will be able to do it. Yeah.
Any other question?
Perhaps it's not really a question, but more. So concerning your explanation as to the different interaction of methanol and ethanol on the surface, you mentioned the different dipole of the two molecules.
Yeah.
I mean, my chemical intuition, for what it is worth, suggests that perhaps the difference is not so much in the dipole, which I believe is there, but
Mhm.
you can also think of electronegativity.
So in the end, they will result in charge transfer.
In charge transfer, indeed. I mean, the way I look at this is in methanol,
Mhm.
you have a less long chain, hydrocarbon chain, and the oxygen, which is very electronegative, will try to suck electrons from where it can, but it doesn't have that much in the molecule from where to rob it from, you see. So it's more hungry for electrons, and it therefore binds strongly, more strongly to the surface, because as a source of electrons that it can take away.
I think in the end it's electrostatic interaction, huh?
Of sorts, yes, but well, electrostatic, everything is electrostatic, right? You have electrons floating around. In the case of methanol, it's likely to be less hungry. The oxygen is less hungry for electrons there because it's already taken them from a longer chain that is bound to. Anyway, just a comment.
Okay, thank you. Thank
Very
you.
nice talk.
Uh-huh.
Thank you.
I think we're done. Thank you all for coming.
Thank you. Thank you for your listening and questions.
I mean, I know that the end of June is a difficult, it's a difficult period to give a seminar, and so thank you for making it.
Okay, I thank you.
Thank you.